Welcome to Introductory Chemistry with Dr. H. This is a video about moles. Specifically, I'm going to talk about what a mole is and why we use it in chemistry. Then I'm going to talk about using the concept of moles to relate the mass of a substance to the number of particles in that substance, and vice versa. And then we're going to talk about the relationship between atomic weight and this unit that we call atomic mass units. And then finally, I'm going to talk about the impact of the fact that elements exist as isotopes in nature, the impact of that fact on the atomic weights that we see in the periodic table. So, what is a mole and why do we use it? Well, let's start with something familiar before we move into something unfamiliar. When we go to the store to buy eggs, we think about buying a dozen eggs, 12 eggs. 12 eggs is a good number. You don't go to the store to buy one egg. What can you do with one egg? If you want to buy eggs, you buy 12 eggs. So 1 dozen equals 12. And it's not just eggs, right? You can buy flowers. Like you don't buy your loved ones one flower, you go and you buy a dozen flowers. So there are things that are of the scale that you can hold in your hand, like eggs and flowers, where it makes sense to buy sort of a group of them, 12 of them. So that's great. The dozen works well for that size item. In chemistry, we're often dealing with particles that are much, much smaller, atoms or molecules. And so if we dealt with a dozen molecules or a dozen atoms, that sample would be so small there's no way we could do anything with it. We couldn't see it unless we used a scanning tunneling microscope or an atomic force microscope. We wouldn't even know that that thing was there. However, if we use a different unit called the mole, which is 6.022 times 10 to the 23rd things, now that sample is something that's macroscopic, something that we can actually see and handle. But that's a lot of things, 6.022 times 10 to the 23rd. That number, 6.022 times 10 to the 23rd, is called Avogadro's number for historical reasons. But we've defined that as the unit that we're going to use to talk about things that are super tiny. Okay? And so that's what the mole is, and that's why we use it in chemistry. A dozen doesn't work for us, or any number even close to a dozen doesn't work. We have to use this giant number. And there are reasons why we use it, and we'll talk about that as we keep going here. So let's see how we can use a mole to convert between the mass of a substance and the number of particles in that substance. So here's a diagram that kind of explains how this works. So let's start with the fact that maybe we have a sample of aluminum, and this is the first example. We have a sample of aluminum. We could say, calculate the number of moles of aluminum we had if we have the mass, little m of that thing, and the mass of a mole of aluminum. So this capital M is what's known as a molar mass, and the units of the molar mass are grams per mole. If we know how many grams there are per mole of aluminum, we can calculate the number of moles as long as we have the mass, and we'll do this example in a minute. We call this number, if we're talking about atoms as our things, we call this unit atomic weight. So it's the weight of a mole of atoms of a particular kind. Once we have the moles, we symbolize moles by a lowercase n. So once we have the moles of something, we know that every mole is 6.022 times 10 to the 23rd particles. So if we want to figure out the number of, say, atoms of aluminum in our sample, we can multiply the number of moles of aluminum times Avogadro's number. That's 6.022 times 10 to the 23rd. That way we can go from moles to the number of particles. And so we've gone all the way from mass of something that we can see all the way down to a number of particles which we cannot see, individual particles, but we know there are that many there based on the mass. Similarly, we can move back the other direction. So if we somehow know the number of particles of something, we can take the number of particles, which is denoted capital N, and divide it by Avogadro's number. We can move back to moles. Once we know the number of moles, as long as we have the molar mass, we can multiply the number of moles by the molar mass, and we could compute the mass of that sample. I'm going to do an example of all those calculations, and you're going to see throughout your study of chemistry that most of the time when we're working with a substance, we're eventually going to get back to moles, so we know exactly how many particles we're working with of whatever that thing is. Right now we're talking about atoms. Soon we'll talk about using the same concept with molecules. So let's go ahead and do this example. So we're working with a 35.6 gram sample of aluminum. So we can go ahead and sort of set up this calculation, 35.6 grams of aluminum. And what I know I'm after here is I'm after the number of moles. And so I need to divide by the molar mass. And, you know, the molar mass has this unit, grams per mole. And so what I know is I have grams of aluminum right now. So what I know is that I need to flip that unit over. You can see that you're dividing by that molar mass. So what I need is grams of aluminum on the bottom of the fraction. So I'm flipping that number over per mole of aluminum on top. Okay, and so this is going to get, and I'll just write the 1 there. So we need that number. Where you find that number is on the periodic table. How many grams of aluminum are there in a mole? So let's take a peek at the periodic table. So here's a periodic table. So it looks like 26.982 grams per mole of aluminum. So you can see where I'm looking right here on the periodic table, 26.982. This number right here, that's the molar mass of aluminum, or the atomic weight of aluminum. That's saying the same thing. So let's go back. So we would write 26 point, what did I say? 0.982, I think. I'll go back and check. 26.982. And that's 26.982 grams for every mole of aluminum. And I flipped it over because I need to cancel grams in this calculation. So if I do this calculation, I grab my calculator, I find that the number of moles of aluminum, and I'll just write all the digits, or a few more extra digits here, 1.3193 moles of aluminum. Now, we have to do a little bit of sig fig work here. We know that this initial number right here has 3 significant figures. We had more significant digits in the atomic weight that we looked up. This number 1 here doesn't, it has infinite sig figs because it's a counting number. And so what we know is that we're limited only by this number right here. So that's going to be 3 sig figs. So it looks like if we were going to report this number, it would be 1.312 moles of aluminum. And this is the N. This is the moles of that substance. So we've gone from mass to moles. Now let's move on. So we know that we have 1.32 moles of aluminum, and do the next step. So we already have done the first step. We know that there's 1.32, right? Let's just check, 1.32 moles of aluminum. And you can leave all those extra digits in your calculator while you're doing this calculation, even if it's multiple steps. So when I did this calculation, I actually did leave all the extra numbers in my calculator. So I know that 35.6 grams of aluminum is the same as 1.32 moles of aluminum. And now what I'm trying to do is I'm trying to calculate the number of atoms in that sample. So now I'm up here to number 2 right here. So I'm going to use this formula where I say I take the number of moles of aluminum and I multiply it by Avogadro's number. So like if you have 1 dozen eggs and you want to know how many eggs you have, you multiply it by 12. So you have 12 eggs. If you had 2 dozen eggs, you multiply that by 12 and you have 24 eggs in that sample. So I have 1.32 moles of aluminum in this sample. And so I'm going to multiply that by Avogadro's number to see how many particles I have. So this is the N, and here's the N sub A, 6.022 times 10 to the 23rd. Avogadro's number actually has more significant digits than this. You can look them up in your book, but usually we just stick with those 4 significant digits. So 6.022, we'll say atoms per mole of aluminum. So this is atoms of aluminum per mole of aluminum. That's what Avogadro's number is. It's the number of atoms per mole. Okay, so we're going to type this into our calculator, and what I see, if I've done this calculation right, is 7.945 times 10 to the 23rd atoms. And again, we need to look at sig figs. We really have only carried 3 sig figs through, so I need to round off at that hundredths place. And so if I was going to report this answer, I would say 7.95 times 10 to the 23rd atoms of aluminum. Okay, so that's an astronomically large number, right? It's hard for us even to fathom something times 10 to the 23rd power. That gives you a sense of just how small those aluminum atoms are. So in a 35.6 gram sample of aluminum, there are almost 8 times 10 to the 23rd atoms, right? A gigantic number, right? That's why we have to use this unit moles, because it gives us a reasonable number to work with. It's much easier to think about 1.32 moles than it is this astronomical number of 7.95 times 10 to the 23rd. Okay, now let's practice going the other direction. Let's say we're starting with a number of particles and moving back toward what the mass of that sample would be. It's kind of hard to imagine like a scenario where you could count the atoms and you're after the mass, but let's just use it as a practice to figure out how these calculations with moles work. So here's another example. Let's say we had 3.72 times 10 to the 20th helium atoms. And so we're given a number of atoms, so we know that we're starting at this side of the diagram. We're given a number of particles, in this case atoms. And if we want to move back to the number of moles, we take the number of particles that we have, capital N, and divide it by Avogadro's number. So like if we had 12 eggs and we wanted to know how many dozen we have, we would divide by 12 because that's how many are in a dozen, and we would find that we had 1 dozen. If we had 24 eggs and we divided by 12, it would tell us we had 2 dozen. So we're doing the same thing. We just have a much larger number of atoms here. It seems like a big number, right? So if we do this calculation, we're going to say 3.72 times 10 to the 20 atoms of helium, and we're going to divide by Avogadro's number. So it's going to be 6.022 times 10 to the 23rd atoms helium per mole of helium. And so what you'll notice here is the atoms helium is going to cancel, and we're going to be left with moles of helium in our unit, because it's sort of a unit that is divided in the denominator, right? And so that will flip up and become the unit in the answer. So if we do this calculation, I find that we have 6.177 times 10 to the minus fourth moles of helium. And it looks like we only have 3 significant figures, so we're going to have to round off at this digit. So when we report this number, it's going to be 6.18 times 10 to the minus fourth moles of helium. Okay, it's important to keep the unit there to make sure that we're all talking about the same thing. So now we've moved back here, and we know the number of moles. If we want to now figure out the mass of that collection of helium atoms, we have to follow this last arrow here, where we take the number of moles that we have times the number of grams per mole, right? So that's going to be the atomic mass again. So we're going to have to look up that number. How many grams of helium are there per mole? That's the number that's reported on the periodic table. So let's go ahead and do that. So 6.18 times 10 to the minus fourth moles of helium is what we got in the last question. And so now we need to multiply that number by the molecular, or the atomic mass. So let's take a look at the periodic table. Let's go find helium. So it's 4.0026. 4.0026 grams of helium per mole of helium. And so what you'll see is the units mole of helium cancels out, and we're going to be left with grams of helium. So if we crank this calculation through in our calculator, we would get 2.4725 times 10 to the minus third grams of helium. Okay, and again, we have to be careful about sig figs. We only have 3 sig figs. So when we do that, we'll see we'll have 2.47 times 10 to the minus third grams of helium. That's the number that we would report. Okay, so now I hope you have the idea. Anytime you're given an element in pure form, you can use the atomic weight to calculate the number of moles of that thing and calculate the number of particles in that sample, or moving the other direction, right? And so I don't think you need to memorize those formulas that are over those arrows. I just think you can think it through. What do you have and where do you need to get? The other thing that's helpful is to think about the units, right? So the atomic weight is in grams per mole. And so if you set up the calculation so that the correct unit cancels, so that you end up with grams or moles, depending on which way you're going. So there we are. So next, what I want to do is talk about the relationship between this thing that I've been talking about, the atomic weight, the number of grams per mole, and atomic mass units. So atomic weight is, as we've said, the weight of 1 mole of atoms of that thing, whatever element it is. An atomic mass unit, on the other hand, is the weight of 1 atom of that thing. And this is a really clever unit system. So this system was originally designed to say that 1 mole of carbon-12 atoms, so a specific isotope of carbon, weighs exactly 12.00 grams of grams. And so 1 mole of carbon-12 is exactly 12.00 grams of carbon-12. So the atomic weight of carbon-12 is 12.000 grams per mole. That's the atomic weight of carbon-12. That's a specific isotope. Remember, in nature, we don't find typically elements just existing as one isotope. The interesting thing is, though, that we can also think about the mass of 1 atom of carbon-12 is also exactly 12.00 atomic mass units. So we've just moved from this macroscopic sample of 12 grams to like the mass of 1 atom. And so if this is the atomic mass, and usually we indicate that as a capital M, that's how many grams per mole, the mass of 1 atom is going to be equal to 12.000 AMU, and that stands for atomic mass units. So when we're talking about the mass of a single atom, we know that that has to be a tiny, tiny number. And so 1 AMU is equal to this number of grams, 1.661 times 10 to the minus 24th. So that's just a tiny number. The way the system is designed, though, if you know the molar mass of something, then you can also easily find the mass of one atom of that thing in AMU, in atomic mass units. And then if you want to, if you want to change it from atomic mass units to grams or kilograms, you have this conversion factor. Okay, and so that enables us to move quickly between the macroscopic and the microscopic size scales. Okay, most of the time we're going to be using macroscopic scales, but sometimes we want to think about that mass of one atom. So let's talk just a little bit more about the molecular weight. We know that elements exist in nature with multiple isotopes. And so sticking with carbon as the example, we know, using the rule that I just talked about, or the convention I just talked about, that 1 mole of carbon-12 equals exactly 12 grams of carbon-12. As it turns out, if you put another neutron into the nucleus and you have carbon-13, that's the other common isotope. It's much less common than carbon-12, but it still exists in nature. 1 mole of carbon-13 equals more weight. It equals 13.00335 grams. So a mole of carbon-13 is a little bit heavier. So what that means in nature, when we measure a mole of carbon, it's going to be some mixture of carbon-12 and 13. So what we need to do in order to sort of calculate the average atomic weight of carbon that we find in nature is we need to do a weighted average calculation. And so we've already practiced using the weighted average thing, but let's talk about it. So in nature, there's 98.90% carbon-12, and there's 1.10% carbon-13. So what we can calculate the atomic weight, or the average atomic weight that we see in nature, just using a weighted average calculation. So the way a weighted average calculation works is you take the percentage of carbon-12 times its weight plus the percentage of carbon-13 times its weight. So let's just set that up. So this is like the percentage of, let's say, carbon-12 times the molar mass of carbon-12 plus the percentage of carbon-13 times the molar mass of carbon-13. That's how it's going to be set up. So let's go ahead and put our percentages in. So when I say percentage, I mean that fraction of 1. So 0.9890 times, and we already know this is 12.000 grams per mole, right? So that's for the carbon-12. And then the other one's going to be 0.0110. That's the percentage of carbon-13 times its weight, 13.00335 grams per mole. Okay, so we're going to end up with units in grams per mole. And so when we crank that calculation through, we end up with 12.011. I'm going to be a little loose with sig figs here. So the average is going to be 12.011. The reason why I added that extra 1 is I know that it's there because that's the number that we find on periodic tables. So I could have added additional zeros on this number and given us more sig figs. So that right there is M. That is the molecular, or that is the atomic weight of carbon found in nature. It doesn't equal exactly 12 because there's some carbon-13 that's also mixed in there. So if we want to know the atomic weight of any element that reflects all the isotopes that are there, we turn to the periodic table and have a look. So when we look at carbon on the periodic table, we see that that average atomic weight is 12.011. So that last digit is the last significant one. So we know that average to 5 significant figures. Okay? And so you can see that those kinds of patterns all over the periodic table. And those weights below the words there, those are the atomic weights you can use to calculate the number of moles or the number of particles using Avogadro's number. So I hope this video helps you understand the relationship between the mass of compounds and the number of moles of compounds and the number of particles in some sample. Today we focused on atoms, but these same principles are going to apply to molecules as we go further on. So hope you found this video useful.